Hello my scholars, you're welcome to my school YouTube channel. My name is Emmanuel and today we'll be looking at the last part of atomic structure and bonding in chemistry. Please stick around, don't go anywhere, we'll be right back. You're welcome back to my school YouTube channel. Like I said earlier on, today we'll be looking at the last part of atomic structure and chemical bonding in chemistry. And under that, we'll be looking at shapes of molecules and solids. What are polar and non-polar molecules? When polar liquids flow from a burette past positively charged rod, the negative ends of the polar molecules are attracted towards it. With a negatively charged rod, the positive ends of the polar molecules are attracted. There's an experiment, a setup. We have a burette on a retort stand, and then we have the solvent, inside of the burette, and then opening the tap, you get a rod closer to the rod. Then you discover that if the end is negatively charged, you see that it will be tending towards a positively charged rod. As the drop of the solvent is coming out from the burette, it will be getting attracted to the rod because of the charges. So we say that is a polar liquid, that is flowing from the burette. So when polar liquid flow from a burette past positively charged rod, the negative ends of the polar molecules are attracted towards it with a negatively charged rod. The positive ends of the polar molecules are attracted. But if a positively charged rod is what is brought near a positively charged part of the molecule that is coming from the liquid, you discover that there will not be any attraction. Instead, it will be deflected away from it. For instance, we have trichloromethane and then we have tetrachloromethane. These are two compounds of methane. Now, one of them is polar, even though they are both compounds of methane. Trichloromethane is polar, while tetrachloromethane is non-polar. What is the reason for this? We discovered that the tetrachloromethane, CCl4, has a symmetrical distribution of similar atoms. Because when we say similar atoms, you can see we have 4 molecules of chlorine, that is attached to carbon atom. If you draw out that you have a carbon atom, then you have, because carbon has 4 bonds, 4 bonds, 4 valencies that is attached. So it will have 4 bonds that will be attached to it. So we have 1 chlorine above, 1 chloride by the side, then 1 chlorine atom by the right, and then 1 chlorine atom down it. So we have the 4 evenly distributed. So that makes it a symmetrical distribution of the similar atoms attached to that carbon atoms. Then the 4 bonds have an equal dipoles. You can see that carbon, chlorine attached to it. We have this. This is the symbol we use in showing that it has a bond, that is attached to it. And because they are equal, they have equal dipoles. We have this on the arrow like that. So each of those equal dipoles, we cancel out each other because we have 4 of that attached to the carbon atom. So each of them, we cancel out each other, and then the compound becomes non-polar because there is no extra one again. So conversely, trichloromethane is not symmetrical. Why? Because the dipoles do not cancel out each other. So this means that the compound is polar. Let's move on to the next slide. A molecule is polar when there is unequal sharing of electrons between the component atoms, resulting in an overall distortion of charges within it. Like I gave you an example now, trichloromethane has unequal sharing of electrons, unlike tetrachloromethane. Tetrachloromethane have 4 equal bonds attached to that chlorine, so they will cancel out each other. So the equal dipoles will cancel out each other and there will be none left. But in case of trichloromethane, there are unequal sharing of electrons, between the component atoms. and that will now result into an overall distortion of charges within that. So because of that, it becomes a polar solvent. So a molecule is polar when there is an unequal sharing of electrons between the component atoms that are attached to the central atom, okay, which is leading to an overall distortion of charges within it. For example, water molecule has the equivalent bonds and the lone pair of electrons contribute to its polar nature. So water molecule is polar in nature because it has covalent bonds, okay. It is formed by covalent bond. We have two molecules of hydrogen combining with one molecule of oxygen. So once that happens and they bond covalently, so as a result of the covalent bonding, we can say that it is a polar. So that contributes to the polar nature. In summary, what we are saying is that the covalent bond in a way covalent bonding in a way contributes to the polarity of a molecule, okay. Consequently, we can infer that there are three factors that actually determine whether a molecule is polar or whether it is non-polar. These factors are: number one, we have the polarity of the covalent bond. That is the first. The polarity of the covalent bond, because don't forget that in the former video lesson we had about bonding, we said that covalent bonding usually takes place among molecules, okay? Molecules combining, unlike ionic, where we have transfer of electrons from metals to non-metals. For covalent bonding, we have sharing of electrons among molecules, non-metals usually. And when we talk about non-metals, they are highly electronegative. And that's why we talked about group 7 elements and fluorine being the most reactive non-metal that is highly electronegative. So in other words, the polarity of the covalent bond in turn invariably depends on how strong, okay, the level of electronegativity of the atoms that is involved, that is bonded to the central atom. So the first factor that determines whether a molecule is polar or non-polar is the polarity of the covalent bond. The second factor is the number and the position of the lone pairs of electrons. We'll be looking at what lone pairs of electrons are. Many students find it difficult to differentiate between lone pair of electrons and bonded electrons. Okay, we'll be looking at the differences between them. So the number and the how many lone pair of electrons do we have, okay, on the neighboring atoms that are attached to the central atoms or on the central atom itself, and what is the position of the lone pair of electrons. And the third one is the shape of the molecule. That is very important. So these three factors actually determines the polarity of a molecule. Let's move on to the next slide. The polarity of the covalent bond depends on the relative electronegativities of the atoms that is involved. You will recall while we're talking about the trends of the properties of elements in groups and then in periods in the periodic table, we talked about electronegativity as the tendency of the atom of an element, of the atom, okay, of a compound having the ability to attract electron to itself. So the electron attracting power of an element, that's what we talk about electronegativity, of an atom is different in different compounds, since it will depend on the atoms to which it is attached. In other words, chlorine can attach to a non-metal, okay, like hydrogen, and then it has a different electronegativity value when compared to the same chlorine attaching to another non-metal eventually. So when we talk about electronegativity, we are talking of an atom, we are talking about electron attracting power of that particular, non-metals. When we talk about electronegativity, usually we refer to non-metals, okay, that are attached to the central atom, since that depends on the atoms to which it is attached. However, electronegativity values can be used to estimate the polarity of different bonds. So the value of electronegativity of a particular atom can be used to determine the polarity of that particular molecule. Let's move on to the next slide now. Generally, bonds between elements of widely different electronegativities will be highly polar. I'll say that again. Generally, bonds between elements of widely different electronegativity. When we say elements of widely different electronegativity, we said examples are only compounds. Why? Because this type of compounds are formed when there is a bonding between a metal and then a non-metal. Okay? And then you agree with me that the electronegativity of the metals compared to non-metals are widely far apart. The non-metals are highly electronegative elements, while the metals are highly electropositive. In other words, they are highly electropositive, but in terms when compared to non-metals, they have low electronegativity value. So bonds between those type of elements, like ionic compounds, because the electronegativity value between them are far apart, okay, will be highly polar. For instance, talk about sodium chloride. Sodium chloride solution will be highly polar because sodium has a lesser value of electronegativity compared to that of chlorine. Okay, so the electronegativity value is widely apart. Okay, so we can say that sodium chloride solution is actually a polar one. Also, bonds between elements of similar electronegativities will be non-polar or only slightly polar and essentially covalent. The bonds between elements that have similar electronegativity, the electronegativity are similar. Okay, the type of bond between them will be non-polar or it can be slightly polar and essentially it's covalent. Of course, non-metals, okay, molecules undergo covalent bonding. Okay, so they will be highly covalent. So if and only if the elements are non-metals, for example, bonding between sulfur and oxygen, both of them are highly electronegative. Okay, this is S2 minus, this is O2 minus. Okay, their electronegative value, both of them are non-metals and both of them actually fall in the same group in the periodic table. So the bonding between them, okay, between these two elements, because they have similar electronegativity, because of that, their electronegativity are similar, they are going to be polar eventually. So if sulfur reacts with oxygen to have SO2, for instance, of course, whatever you are going to have, because they combine or they are bonded together covalently, they are going to have a non-polar molecule. Let's move on to the next slide now. In non-symmetrical molecules, when we talk about non-symmetrical molecules, we are talking about CHCl3, for instance, okay, because they are not having equal number of dipoles. Okay, even if one cancels out, we still have extra one that is left in that molecule. So it is a non-symmetrical molecule. So HCl is an example of that. When we talk about HCl, this is, you can see the state gaseous. So which means this is hydrogen chloride. Okay, I told you the other time that if it is HCl aqueous, that will be hydrochloric acid. But if it is HCl gaseous, it means that it is hydrogen chloride. So hydrogen chloride is a non-symmetrical molecule, and then water is also a non-symmetrical molecule because the center of the positive charge and the center of the negative charge do not coincide at all. So that is why they are non-symmetrical molecules. So the polarity in these molecules, that's water and HCl, is due to the presence of highly electronegative elements such as oxygen and chlorine. So by default, this is H2O, an H2O molecule, and then hydrogen chloride. Both of them are non-symmetrical, and because they are non-symmetrical, what makes them non-symmetrical? Because the center of the positive charge and the center of the negative charges do not coincide with themselves, and because both of them have highly electronegative elements. Okay, there's a presence of highly electronegative elements. You can see chlorine here. Okay, it's highly electronegative. You can see oxygen here, highly electronegative. Okay, because of the presence of the highly electronegative elements, okay, the polarity of this is so high. So we can say H2O is a polar molecule. HCl is also a polar molecule. Let's move on to the next slide now. Let's see the difference between bonding pair and lone pair of electrons. What's the difference between the two? The valence electron configurations of the constituent atoms of a covalent compound are important factors in determining its structure, in determining its stoichiometry, in determining its properties. For example, chlorine has 7 valence electrons. Okay, in the outermost shell it has 7 electrons, so which means it needs just 1 electron to complete the octet rule, okay, of the group O element. So it is 1 electron short of an octet. So if 2 chlorine atoms share their unpaired electrons by making a covalent bond and then forming Cl2 chlorine molecule here, they can each complete their valence shell like we have it here. This is the outermost shell electron. We have 1, 2, 3, 4, 5, 6, 7. We have 7 of this chlorine, okay, atom, and then combining with another chlorine atom because they need to satisfy the octet rule, okay, by having 8 electrons in outermost shell. So both of them will bond together and share their electrons. And in bonding, we said it's covalent, that sharing of electrons are actually. So by the time they come together, they share electrons. So you can see now this one and one here, they are here now, they have shared it. So for this chlorine atom, we have 8 electrons, you count 8. For this also, you count 8 this way. So both of them are certified. Now, each of this chlorine atom now has an octet. The electron pair being shared by the atoms is called a bonding pair. This one electron we have here now, these are the bonding pair, okay? They come together and then they bond, they form the bond. They are the one that participates in the bonding itself, okay? That is the bonding pair. But the lone pair of electron, which is the other, 3 pairs of electrons, that's this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. For each of them, 6 of this like, those are their lone pair of electrons. They are just a lone, okay? They are not joining in the bonding like these two now coming together where they share electrons. So these electrons that are being shared together, when they combine together, is what we call bonding electrons, while these other electrons outside here that do not directly participate in the bonding are what we call the lone pair of electrons. Lone pairs are not involved in covalent bonding. Let's move on to the next slide. Shapes of simple covalent molecule. The shapes of molecules and their bond angles, that's the angles between the covalent bonds, actually are not random, but they are determined according to a set of principles called the VSEPR. VSEPR stands for valence shell electron pair repulsion. There's a repulsion, okay, between the electrons, okay, cloud, among the electron clouds that are revolving around the shell, around the nucleus of electrons. So there's a principle, we call it VSEPR. VSEPR is valence shell electron pair repulsion theory. We will consider a simple molecule as consisting of a central atom around which a number of other atoms are arranged around it. There's a central atom. That's the one that is bonding to every other atoms that are around it. Okay, we have a central atom and then they are arranged. Then the outer shell of this central atom will contain electrons which are part of bonding pairs and may also contain lone pairs also. It is the mutual repulsion between these electron pairs that gives the molecule its shape and bond angles. Take note of that. The mutual arrangement, the mutual repulsion, okay, electron repulsion, okay, between these electron pairs is what gives the molecule its shape and then the bond angles. The VSEPR theory states that, number one, electron pairs repel to get as far apart as possible. Of course, they have the same charges. Because they have the same charges, and like charges will definitely will repel, while unlike charges will attract. So they have electrons negatively charged, so they will be repulsed. There will be repulsion, okay, between these electrons that are rounded. So the VSEPR theory states that firstly, electron pairs repel to get as far apart as possible, and secondly, lone pairs repel more strongly than bonding pairs. Of course, lone pairs will repel because they are the same. They have the same charges. So they'll be repelling more compared to the bonding pairs. Let's move on to the next slide. Think about, how are you able to hold an object in your hand without it falling off? Why does it follow? You hold an object, why does it fall off from your hand? Just like this. Okay, an object is held this way, and then you can see this also held this way. What gives an object its sense of boundaries? These are questions you think about. If you hold water in your hand, of course, water cannot stay. It will what? It will flow out. Okay, but when you have solids held like this, you can hold it without falling off. What makes you, have this, sense of boundaries? Number one, it's as a result of electron-electron repulsion. There's repulsion between the electrons in that atom. Okay, the electron cloud is there. Okay, so they are repulsing because they have the same charges. Okay, and then negatively charged electrons in an atom repel each other. That is what actually determines the size of an atom. The same principle is applicable to the shapes of molecules. You can tell what gives the shape of a molecule what it is. It's because of the repulsion between the electrons in that cloud that actually gives the shape of the molecule to what it is. Now we've come to the end of the preview of this video lesson. If you want to have access to the full video, please click on the link in the description below that takes you to my school website where you have access to subscribe. Please subscribe. And in the full video, we'll be looking at the different shapes of molecules, covalent molecules, the shapes of crystals. Are they ionic? Are they covalent? Are they molecular? Are they metallic? And so on and so forth. I believe you enjoyed this content. If yes, please don't forget to click the like button, hit the subscribe button, and finally tap the notification bell to keep you informed once we upload our next video lesson.